Hi, I'm Łukasz. I come from the internet. I usually say that when I'm away, but like here, very close to Poznań, should come visit when we're done with all the renovations that we have. You have a much nicer Christmas spirit here than we have in Poznań. All right, I used to have a Twitter handle here, but like apparently Twitter is kind of, you know, on fire right now, so Mastodon, the future, okay? Today we're going to talk about a problem that a lot of people have with Python. It's that it's slow. But when is it slow? Like, what is happening? Like, why are we having problems with our interpreter language? Well, depending on what you're trying to do with it, right? So a very common issue that people have is when they have some data sync. So, you know, like you're just feeding some data into a service, and it just takes too long for this data to be fed. So that's one kind of the typical, I don't know, like architectures or archetypes of what we're going to talk about today. Another one that I'm mostly familiar with, since it's, web, is when you have a request to a server and you expect some response. Usually that's HTTP, not always. Sometimes there are connections, yes, because we have WebSockets and whatever, but usually it's some kind of request that you have. And there's usually only a couple of kinds of those requests, and they're kind of, well, different because of their parameters, but usually it's kind of typical what you want to do with here. And then the third kind, well, you have some computation that needs to be done, and there's gonna be some answer later after the fact. So maybe you can think about it as a special kind of request response, but usually that involves like looking through like some big data, this sort of thing. So something that won't easily fit in some like database query or whatever. So all those three issues are real, and people have problems solving them in Python, and they have different solutions. But the one that I'm going to be showing here mostly is one that I see kind of underutilized for how powerful it is for making things that you didn't think your computer can do actually work. So first of all, let's just address the GIL in the title of the talk. So I had this issue a few years back when I still worked at Facebook, where we had this CPU leak. It's like, what is that even, right? Like we had a application that in time, as you ran it, would respond slower and slower to user requests. So we saw that, you know, kind of, it doesn't really do much. It doesn't really, it's not about the requests being more complicated in time. They were in fact like the same, but still it took longer and longer, as in the green line that you can see here, for the server to process this. And we were like flabbergasted, like, you know, and if nothing, what we're doing in this very simple application, just 2 threads, actually does anything special. It's mostly just idling. There's nothing that is supposed to cause this sort of stalling. So then it turned out that, we had a logging library that also used a thread in Python, and it was something that was just provided for us by infrastructure. We just used it as a dependency on every project at Facebook, essentially. And somebody made a change, and that change did not clear up data that it was aggregating. So this data set for this logging that we were matching became bigger and bigger and bigger over time. So every time you try to match some log line, like it took more time. And because of the global interpreter lock in Python, the time that could be spent on your actual code just decreased over time. So yeah, we do have this global interpreter lock in Python, and that causes us to only be able to use a single thread for Python computation at any given time, right? So even if you have many of them in your application, only one piece of Python code runs at the same time in one Python process. Global interpreter lock means there is one lock per process. It is still something that we have today, and you're likely going to have it into the future because it is an important feature of Python that is used to protect the internal state of the interpreter from being corrupted if multiple threads would start changing it. And in fact, which is ironic, well, the construction of the global interpreter lock means there's only one. So ironically, it is pretty fast at what it's doing. So it is limiting us from scaling into multiple cores, but it is very hard to replace this single lock with fine-grained locking in ways that will be more performant. This is why we had attempts to remove the GIL multiple times in Python and they failed. Well, the removal itself is something that is doable. It's been done 2 times at least successfully as far as I am aware of. However, to make it actually faster than what we have now, not so easy. So the GIL is there and we have to live with it probably into the future, and especially with the versions of Python that are already out there that you're already using. So can we do anything with Python that needs some level of concurrency even with the GIL? And it turns out that yes. Like an observation that people have very often is that, you know, if you have this request response typical HTTP server workload, some data that you're waiting on, and you're just waiting, you're not doing much because it's some external source. Instead of waiting on this data serially, you could maybe split it and wait on it at the same time so that the page render happens quicker. And in fact, like if you start doing this, what you're doing in practice is more like this thing, where instead of doing everything serially, you do everything concurrently, right? And this is what asyncio is all about. It allows us to utilize a Python interpreter with a global interpreter lock in a single thread in ways where instead of wasting time waiting on I/O to happen, what we do instead is we do something else in the meantime, right? So the goal of asyncio is to maximize the usage of a single thread. If you want multiple threads, just use many asyncio, so use many Python processes. By handling I/O asynchronously and by enabling concurrent code using coroutines. We're not going to talk about I/O asynchronously today because, yeah, it's PyData. We're going to be talking about concurrent code with coroutines. And the reason why is that it turns out asyncio is great for orchestration of work that is happening somewhere else. And it doesn't particularly matter if that orchestration is a database driver or some CPU-intensive computation in a different process. So yeah, we have asyncio. I'm not going to do a primer here. I'm not going to teach you asyncio in 5 minutes. It's unreasonable. I've done a series of videos for a previous employer that are still on YouTube. So if you just look for them, like, people seem to be happy with them. And if not, there's a lot of material on, like, you know, asyncio 101 style thing on the internet. Or I can answer questions if you have them, you know, kind of anywhere outside of this particular talk. Here we kind of assume you're not going to be scared of seeing await. We're not going to be doing much advanced asyncio today, so don't worry. It's simply, there's async functions now, async defs, and you can await on things. That means our code is waiting on something to happen, so the same Python process can do something else in the meantime. All right, so we have a data sync, or we have a request response, or we have this map reduce problem. And how does asyncio let us fix this? Well, I work best if I am faced with examples. So let's just try an example. This example, before we begin, because like I personally, I get very easily distracted by like things that I understand why they happen in people's code. So just to get that out of the way, this is not important to this talk, but you know, we're going to use a function that says mem usage, and it simply says what the current memory usage of a process is. I'm using tracemalloc for this because tracemalloc is good at you know, tracing allocations in a Python process. And the print that we're using looks like the built-in, but it's not. It's a little changed so that it's colorful and it shows us our process name and how much time has passed since we last printed on that process. It's going to be just super simply useful to just see how long time is spent on an operation. So yeah, with that out of the way, we will use big data. We're going to generate some data, like nothing very interesting. It's a totally synthetic, data frame. There's just a bunch of records where the second column there is some number, but maybe not really. So there's some not a number there. But what we want to try to do is to have this big data set and just generate a sum of all those values in the second column, right? So here the function that generates the data doesn't do much interesting things. You probably have seen that many times where, yeah, there's a data frame, we convert it to records. That's it. So having that in mind, we generate the data. What I did is I generated 2 billion records so that it barely fits in my memory on the laptop. So it's like 64 gigs on the laptop. So yeah, peak memory usage 50 gigs. Yeah, we should be good. So yeah, there's a 45 gig pickle file that we're gonna be reusing. Since generating this is a little time consuming, probably this for loop right here is stupid, and I could have done it much better with this sort of data size, but it's simple Python, doesn't matter. I've done it once, and we're just gonna reuse it later on. So okay, we have a 45 gig file, and we want to make a sum. So if you only do this with one process using a very simple function, essentially there's a function that uses NumPy's nan sum. There are two problems with just doing this in asyncio. So first of all, if you are making operations that are time consuming, like in NumPy, some of them, not all of them, some of them can actually drop the GIL saying, I'm doing this in C, so I'm not holding the global interpreter lock, something else can happen at the same time. And that is wonderful because asyncio, if it's, say, a web service, like, I don't know, like something to analyze, whether your photo of a brick is this Lego brick or another one, that will still work. But if that operation is blocking, then the entire service is now waiting on this one operation and no other request can be handled at the same time. So this is not what we want. So we want to delegate time-consuming operations that are blocking with asyncio to a different process. So the easiest way to do this is to just, have some workers with multiprocessing. And here, like, this is only the if main boilerplate, right? So again, I'm just doing this for myself because otherwise I would be, instead of listening, I would be wondering, like, how is this being run? Like this. We have to start trace malloc, we load the data from a pickle file, and we do asyncio.run with our main that I'm going to show next, right? So it should be pretty simple. So the main starts a ProcessPool Executor with a different kind of workers. We're going to be talking about, how many workers should there be. There's going to be some batching, and then we're running our process function, the one that we saw like 2 slides back, in an executor. So in this ProcessPool, right? And then the only thing that is actually very asyncio here is that await asyncio.wait of all the batches. This is where the magic happens. We're waiting for all the executors to complete their tasks. So yeah, we can set the workers to 1, we can set them to 100, and we can see which number is going to be fast, which number is going to be slow. So let's try it with just 1. And if we just try it with 1, we see that, well, it's not particularly fast. It takes 150 seconds to just do this sum. So like it's measly, it's not very interesting. So, well, I have a multi-core CPU, right? Let's try 4. So 4 in 4 batches. So each worker gets 1 batch. And 69, nice. So okay, that's better than 150. But I have actually 10 cores in this laptop. So let's try 10. So we tried 10. Okay, there's more happening, but it's still 69 seconds. So that kind of sucks. Like, why didn't it do much better? But in fact, if we look closely, like, is it really doing what we wanted? Well, if you look like it takes a long time for any worker to even receive data. Oh, it's because we serialize and deserialize data, passing it back and forth to processes. So obviously it's pickling, and it's not pickling 45 gigs, but it's pickling 4.5 gigs. So it's still pretty, wasteful. The worst thing about this is that, yeah, we have 10 processes that are workers, but we only have one that orchestrates the entire thing. So while it is busy serializing work for one worker, all the others have to wait. They cannot do anything. And if you move later on and see how much time do they actually spend processing, well, it's way less than what the serialization and deserialization takes. So obviously this is a problem. And that means by default, if you're just using multiprocessing, or if you're using process executors with concurrent futures, or if you're using process executors with asyncio, it doesn't help you, right? So you need to do something else. And that, okay, I almost forgot. So there's many arrows to remind me. I have 64 gigs of RAM in my laptop. I'm very impressed by this. So yeah, it's a lot. But if I have 10 workers and each of them uses 4.5 gigs, and they would be actually parallel, because now they're not. So I barely scrape by. But if it worked, that would still mean like I don't have enough memory in my computer to do this locally. So memory usage also terrible. So clearly we need to do something else. So maybe we can use copy and write. So what is copy and write? Well, not all operating systems, like macOS, not great at this, but Linux, awesome, have this thing where if you start a process and then fork the process into another one, into some child process, then by default, unless you change memory of the process, it just says, okay, like you can just reuse it. You can read what you already have there. We don't have to copy. It's not just so that you save RAM, but it's mostly because it takes time to copy the RAM. So forking is much faster without having to copy the entire memory space of a process. So in theory, that is great for us. And that is something that could be easily used for this, where if we already read the data somewhere from the internet, like, some user sent us a request with 45 gigs, we just fork and we can now process, right? Like in theory, that's great. But in practice, in Python, this is an issue like I filed, 5 years back, that like in Python, even reads are in fact writes to memory, because we have a garbage collector, and that garbage collector tracks what is used and what is not used. So to work around this in a server model, that's something used by Instagram, for example, like you can just say, okay, I'm setting up all my libraries, I'm importing everything that I want to import, and now I'm freezing the garbage collection, meaning this memory will never be freed, but that's just my libraries. I actually want them in the memory, so that's fine. And then I fork. So at least that frozen memory will still be left intact. It's not going to be copied. But that doesn't really help us because we're getting new requests, and this is data that comes with a request. So we can't really keep freezing it because we would run out of memory anyway. So copy and write, not really helpful there. So shared memory, something that is amazingly working on all the platforms I tried, and I was pretty sure this is have to be, only maybe Linux does it, because otherwise people would use it, right? I don't know, but it works even on Windows. It works everywhere. So what you can do is, instead of passing data around by pickling them, we can convert our data into a representation that is shareable. So you create a shared memory block. How big should it be? Well, that depends on the application. You could maybe just do like 50 gigs, and maybe it'll fit, maybe it won't. In our example, I just say, let's create the number of bytes that we got in our data, right? For like loaded from the pickle file, so it's going to be 45 gigs. But the point is, now we have a representation of an array where the buffer that we're using is the shared memory buffer. So we're not actually, kind of copying the data like, what am I trying to say? Oh, okay. Like we're not creating an entirely new array every time. Like we're just copying the data once because unpickling does not support shared memory. So if we wanted to put data from disk straight to a shared memory block, that's still a feature that can be added maybe by you to Python. Currently, what we have to do is to load this data from somewhere and then put it in a shared memory block. But once we do, we never have to copy that data again. The one single copy is straight before the deletion of the original like object. And we delete it because it would otherwise be a lot of wasted memory. Amazingly, that's like 45 gigs plus 45 gigs, so that's more than I actually have. But by the magic of virtual memory allocation, like it all works out, and you know, like the computer doesn't really complain. No swap is being used. That is just fantastic. So yeah, our if main got a little longer, but fortunately, everything else will also get longer. Sorry, it's just, you know, it's just a complication, but it's gonna get faster. So the other thing that we need to do is in our main method where we actually process our things, what we used to do is we took our data and we just sliced it and passed it to a process executor. And that every time behind the scenes was pickling the data and unpickling it on the worker process. We don't want to do this again. So we will not be passing data. What we are going to be doing instead is we will be passing only information about the fact that, hey, there's some shared memory for you. What the data is, it's the name of the shared memory block, the shape so that we can actually attach some NumPy array to the raw buffer, and the D type so we know like how we can read it in Python. And still we have our offsets, right? So this I and batch size only so that we don't, you know, reprocess the entire thing on every worker. We still want to split the work so that it's good. Okay, so that's what we needed to do here, but those are arguments to the process function. So process needs to change as well. And that's interesting because that function is actually the one being executed on the worker processes. So what are we going to do? We don't get data anymore. Instead, what we get is this shared memory name, some shape, D type, offset, batch size. So we have to actually create a shared memory object with a given name. That means on that single machine, on that single computer, it will find that, oh, okay, I matched the name. I have access to this memory, good. And now we can do the same thing where we recreate the array from the shared memory buffer. We don't have to copy anything anymore. The data is already there, right? So now we can do the non-sum on the data we have with actually just the offset that we want, since we don't have to summarize the entire array. Okay, and send the result back. So how does this do? Well, it only takes 6 seconds. So I would say success because it's like easily what, 11 times faster? But there's more. Like all of this should excite you because, you know, like we fixed actually everything that was wrong before with this naive setup at first. So first of all, like you can see that receiving the requests from the orchestrator, from the main process now takes literally no time. Like, you know, it is below 1 millisecond, you know, it's very fast. Second of all, when we actually start doing something with the shared memory, that takes what? Like less than 100 milliseconds. So setting up the shared memory block inside the worker process is also very quick. And better yet, now you can actually see some parallelism, right? Because we received the requests at the same time and the workers actually started computing data at the same time and sending results back. So yeah, like this is essentially what we want to see. Better yet, because the non-sum only still did the windowed computation, the peak memory usage is now like only like what? It's 5 times smaller than it was before. So okay, cool. That essentially solves our issue for the most part. But we now have to actually set up the shared memory block at first. Right? And this is some additional time that we didn't have to spend before. Now we have to copy things over. So first things first, like if we make pickle ever work so that it can put data directly to a buffer in shared memory, that will be faster. But also sometime is literally the operating system just creating a multi-gigabyte like shared memory block in RAM. So if you set up only one at the start of your application, easily a third of this time that is spent here, like will be, just spent once, and you don't have to do this again. But then when you're getting requests from your clients, like that's still something where we need to copy data. It's annoying, but it's what it is for now. But that's still, even if you count the entire setup, which I don't think the entire should be counted, but if you count the entire thing, still easily 3 times faster than what we did before. And obviously our non-sum is a silly example. For an actual example where you actually crunch some data, like you would spend much more time on the worker. Like the kind of pathological example here where we spend less time than pickling, like was maybe used to just show that, the pickling is wasteful. But it will be even better if you're actually spending a lot of time doing computation. Okay, so now we have shared memory. Why is it cool? Because you don't have to serialize and deserialize wastefully. You can achieve true parallelism now because we have shared data and it can be read at the same time. There's less overall memory consumption, so all good. Well, but is it only readable? Can we change the data? Yes and no. So what we had before was some buffer where there's just like random bytes there. And NumPy made sense out of it by us telling it, this is the shape it has and this is the D type it has. If you start mutating this data, in parallel in the same spots, you might corrupt it. That's why the global interpreter lock was actually useful, right? So you don't have that anymore. So you have to think about this in your application. If your application is sort of simpler than like you can make do with just a bunch of types that Python provides, you might use something else that the shared memory submodule of multiprocessing has. And to show this, I'll show you a Windows shell, because why not? We have 3.11 right now in Windows Store. It's not the one by default, but if you look for Python 3.11 in Windows Store, you'll find it. So we created a shareable list, and those lists can have strings, bytes, numbers, nonce, trues, and we use the same name on a different process, and boom, we can now access it. So that's pretty cool. This is actual shared memory natively on Windows. Like I never thought that this was possible, but it is. This is cool. However, if you try to put like some random objects there, it will, blow up with a very unhelpful exception to boot. So, like no, you cannot really pass anything. So you need to be careful about the types of data you want to pass. But if you can somehow figure out like, if I just serialize it just right, like you might make do with this. So for example, here, like we just use the timestamp instead of the entire datetime object, and we can now use that same data to just create a new datetime object on the other side to actually see the same information on both ends. So you can make do, right? But now you're kind of in the serialization, deserialization game yourself. But what the shareable list gives you is that now the changes to indexes in the list are at least atomic, so you're not going to destroy the list by having it mutated from 2 processes at the same time. With the NumPy structures sharing the same buffer, it might be way more tricky. So this is safer if, like, all you want is to for multiple processes to communicate with one another. Okay, and the last thing that I wanted to show is that, okay, like here we have Windows Subsystem for Linux. So yes, we have macOS, we have Windows, we have Linux, Windows, but still Linux. So yes, all those things work on the 3 platforms, so you can use it. But the actual last thing I wanted to show is that the example that I gave before, it worked because it was carefully designed to work, but the world does not work like this. Like every now and again, you're gonna have issues, right? And now asyncio can really help you with recovering from those issues. unless you don't really program it in a way to for it to help you. In which case, the thing that we have right now can sometimes blow up, right? Like, you know, you can have, I don't expect you to be able to read this. Like, what is happening is there's a value error somewhere in the worker process. So it gets bubbled up as this remote traceback to you. The process crashes, like you don't get any summary of anything. The process is dead, like we're done. Why is that happening? Well, because, for example, if there is an exception in the process, in the worker process, we have to somehow recover from it. We have to catch it somehow and we need to react to it. So this is entirely possible in this kind of classic way of doing things in asyncio. One thing that we have here is this assert that we don't have any pending tasks, so everything actually finished. And then we could put a try except around the result in the for loop that is like on the bottom, so that if there is an exception that we gathered from the worker process, like now we will catch it. The problem with that is that there might be many exceptions that might be risen. And maybe if even one of them happens, waiting until everything finishes is not really a good use of our time. So we can now configure the asyncio wait instruction like we have a wait on. However, you have to now change the code below to do error handling differently. So in the end, what that meant is that classically in asyncio, error handling worked if you were really careful, but you always forgot an edge case. You always forgot to put, you know, some error handling where it's supposed to be. So now in 3.11, things became more uniform. They kind of look weird at first, as with anything asyncio, but once you get a hang of it, it is much easier to write correct programs. So what you do instead is you create a task group. And within that task group, you don't await on anything. Well, you might await on things in that async with block, but the main work happens when you create tasks on the task group. So the tg.createTask, it's where you actually put things to do work. The nice thing about this is that you don't really have to await on anything, because this async with will itself only exit. The block will exit when all work has been done. So having this, the situation is already better because we get a nicer exception. Oh, this is not what you expected, right? Yeah, but it's already an improvement because now we have an exception group with every exception that happened grouped for us at the same time, which is useful because you can see the entire kind of bird's eye view of our error handling. But better yet, you can actually react to it by using exception groups except star that we have right here. So we can get any value error, for example, if we expect that this might be an expected failure, and just, I don't know, iterate over the exceptions in that group, because the VE here is not really a value error instance, it's an exception group that contains one or more value errors. So we can iterate over it, we can do something, we can recover. But the nice thing about this is that getting outside of the task group means all the tasks are done, nothing can be pending. We can really now assert that there will never be a task that is not done afterwards. Some of them, and this is a feature, will be cancelled. What that means is if we had exceptions that we did not anticipate, like it's like a transaction, like everything is being cleaned up for us. So all the kind of, well, like resources that we might be using are going to be cleaned up after us. So that is a big improvement. Like, it looks weird, but you know, you only create those task groups in your code a few times. And the nice thing is that the cancellations, the exceptions that can occur, are both the unexpected kind and also the expected kind. Like, if you are running your program for an hour and you're seeing, I expected this to finish in 10 minutes, but like it did not. Like it did not. Like, you can now Control-C and it'll actually shut everything down. Like in multiprocessing, this is a large issue where you're trying to Control-C the thing, but it does not really listen to you. So with task groups, that's no longer a problem because a canceled error is treated like any other exception. Everything else is canceled, cleaned up for you. You can now recover. You can now do something with the exceptions if you decide to. So the end result is now
okay, I received a bunch of requests, but there were value errors. Now the total sum at the bottom is 0 because the transaction, you know, like air quotes, is entirely canceled. So that's a, you know, way cleaner situation than what we had before. I understand that I mostly talked about shared memory today, and this is the actual takeaway of the talk. But if I got you kind of curious about task groups and about exception groups, and you're like, okay, cool, but I still don't get it. Like, I actually did a talk just on that. So just watch that. It's same length as here, but only about exception groups. It's a kind of a complex topic, but like once you get it, I'm really excited about like using 3.11 right now. So okay, so that's me. Let me show you my face once again. Thanks for having me. It was a pleasure.